So a bit about me. My pronouns are he, him, or they, them. I work at SUSE, and my background before coming to Rust was mostly Python and OpenStack, and afterwards Golang and Kubernetes. And mostly, I nowadays I use Rust, Go sometimes still to and C, and I still mostly work with Kubernetes and container-related topics, and sometimes with Linux kernel, and of course a lot of with BPF. I will start with the short introduction. What is eBPF? And eBPF is a mechanism in Linux kernel which allows to inject programs which are triggered by various events or integration points in the kernel. And one of the most popular triggers for BPF programs in Linux kernel is network I/O. And there is, well, the most known projects which is using eBPF it's called Cilium is using it, for example. There are also a lot of projects which are using eBPF for tracing functions both in the kernel and in the user space. And yeah, like tracing some function calls is also an event, a trigger, which BPF program can be triggered by. And the last thing I'm mentioning here, for me, very interesting one, are LSM hooks. And LSM hooks are custom hooks in the kernel code, which allow to create a security system which is denying or allowing some action. And if you know SE Linux and AppArmor, for example, these two security systems are in fact using LSM hooks. Uh, but nowadays, since kernel 5.7, you can use those LSM hooks also for creating BPF programs. So you can, in fact, try to create your own security system similar to, let's say, SE Linux or AppArmor by writing your own BPF programs and not doing any change to the upstream kernel source codes. And BPF programs are at the end compared to the bytecode. You can also write BPF assembly, but for example, I've never done it. Mostly people write BPF programs in C, and then the C source code gets compiled to the BPF bytecode by LLVM. But nowadays, there is also a similar possibility of doing it from Rust. Since Rust underneath also uses LLVM. So at the end, LLVM is still used to convert the Rust code into BPF code. Although I'll come to that later, but yeah, the BPF programs are supported in Rust, but it's still super early, super experimental. There is not yet any project which would be used on production, which is developing BPF programs in Rust. Yeah, like in the most known projects, it's still done with C. And well, some sorts of BPF programs are like tracing events or getting information about events, and some of them can make actual decisions, what's happening with some events happening in the kernel. And well, I mentioned that probably the most popular kind of BPF programs are the network ones. And in case of network BPF programs, you receive the events from the kernel that, oh, some packet came to the network card, or there is a packet which was parsed by the kernel. And in that case, you can make an actual decision whether you allow that packet to come, whether you redirect it somewhere else to some other network interface, or maybe you just want to deny it and not come to the down, yeah, go further anymore. But the other interesting kind of BPF programs which allows you to make decisions is, as I mentioned, like LSM BPF programs. And LSM hooks are very various. You have like a bunch of LSM hooks triggered by I/O. You have LSM hooks triggered by creating a new process, someone trying to log in as some user. There is really there is they are really various, and to all of them you can write a BPF program in which you make a decision whether you want the particular action to happen or you are going to deny it. And well, when you use BPF, you write BPF programs, and then you need to write a user space program which is loading BPF programs into the kernel. And loading of those BPF programs is done by BPF system call. So yeah, usually when your project consists of two parts, and yeah, one is set of BPF programs which are usually compiled to ELF objects, and then you have user space part which is loading them into the kernel. And BPF has a concept of BPF maps. They are data structures in which BPF programs can store the data, and those BPF maps can be also shared to the user space. And there is a directory sysfs BPF in which you can pin those maps and let user space programs to interact with them. And well, I will start with showing how BPF programs look in pure C before going to the Rust examples. So I will most likely have to increase the font, right? So okay, yeah. Yeah, the example in C is here. So we have a very simple BPF program. Oh, it's, yes, like that. Okay, so it's a very simple BPF program. Why are Discord's notifications popping up? I don't know. It should be turned off. Okay, I hope they will be gone right now. But anyway, so there in kernel there is a function called clone, which is called every time we are creating a new process. So basically, when we are doing fork in the user space in the kernel, we end up with the clone function being called. And we have here fentry type of BPF program, which is tracing some function when we are entering it. So at the moment of call. So this BPF program is attaching to the clone kernel clone function. So it's getting triggered every time when we start scheduling some new process. And in this program, I'm only getting the PID of the process scheduling the new one, writing that PID in a BPF map, and logging the fact that something like that happens by BPF print k. And this structure here is a BPF map in which I'm storing PIDs, and here I'm making an action of saving the particular PID into that BPF map. And here I'm getting the name of the process. So com is like a name of the process in the kernel, and yeah, here is just logging. And there is a user space part, which is loading that BPF program. LibBPF, so the library in C, which in which you are writing both BPF programs and loaders, has a concept of skeletons. They are auto-generated, so that header is auto-generated. You instantiate that skeleton, attach the BPF program, and then yeah, to keep the program alive, a BPF program alive, you have two ways. You can either keep the user space program alive, and as long as the user space program is alive and we don't catch any signal here, the BPF program is alive. But if we want to keep the BPF program alive, even after our loader is not alive anymore, we need to pin the program in the BPF file system. Yeah, here I don't have an example for that. In this example, the BPF program is dying immediately when the user space component is gone. So I'll run. Let me run it. Yes, yes, yes. I will end here as well. Like this is fine. Okay. So yeah, I have three examples already here, but I will go to the one in C. I will compile it. Oh yeah, it's already compiled. And yeah, just to show it, I will remove the output and compile it again. And important thing is that to do anything with BPF programs, you have to be root. So we need to execute the fork trace because that's the name of our program is roots. Successfully started, and now in the other terminal we can use the tool called BPF tool to check whether the program is really running. And we see it here. We have a tracing kind of BPF program whose name is kernel clone. And we can check the logs of BPF programs by doing BPF tool proc trace. And here we should see our output that, yeah, some process is forking. So we have bash forking, we have Chrome forking, XDG, dbus proxy, and other processes doing forks. And we are also saving the PIDs in a BPF map. So we can look up for BPF maps. We have only one BPF map in the system, which is called processes, so it's ours. And we can dump the map by name processes. And yeah, we have PIDs. I was in the program, I was assigning value 0. I was interested only in storing PIDs as the key. So here it is, the proof that it works. And yeah, the presentation is mostly about Rust support. I showed how it works in C as the reference point. But there are two ways and two separate libraries in Rust which deal with BPF. The first one, the more popular one, and in fact official, because it's like affiliated with libbpf, is literally like libbpf/libbpf-rs on GitHub. So it has pretty much the full coverage of BPF features and BPF programs. But the thing is that when using libbpf-rs, only loader user space part is written in Rust. BPF programs themselves are still written in C. So when you are using libbpf-rs, you maintain both C part of code for the doing stuff in the kernel and the Rust part for loading and managing. But there is also more experimental library which allows you to do both things in Rust, which is called Aya. It's really cool, it's really promising, but not every type of BPF program is supported yet. And yeah, it still requires nightly Rust. And I'll start with showing example of libbpf-rs, where so in case of libbpf-rs, the BPF program is still the same in C. It's even assembling here in this example, but we have main RS module which is using libbpfrs to load the program. Whoa. What happened here? Okay, now it works. All right, so yeah. So libbpfrs automatically generates a skeleton from the C source. So that fork trace scale builder is a structure which was automatically generated from that C code. And yeah, you open the skeleton, you load it, and then you have that skeleton is providing mutable references to all the BPF programs in the particular module. Here we have only one, so we are just picking the kernel clone from Proxmood. We attach that program, we attach the link, and yeah, after that line, the program is loaded and it's going to be kept alive as long as the user space process is going on. And yeah, here is just code for like handling signals and like showing dots as long as the program is running. So yeah, let's check this out. I will go to the upper directory and libbpfrs example. Here we have it. I will show how is it building, and there is a custom like cargo extension which we are going to use with libbpfrs. It's so we will do cargo libbpf. So there is a libbpf cargo module, and by doing cargo libbpf make, we are firstly building that skeleton from the C code of BPF program, and then we are building that main rs program. So it's doing it by two steps, compiling BPF objects and like generating that skeleton, and now we are actually using like the main cargo for compiling everything. It will take some time. All right, so it's here, and now we should have the ready to go binary, which we can spawn in target debug fork trace. That should be it. Yes, and it's it. So let's check out what BPF programs are loading. And here we have that tracing program, and we have also maps, and we can dump the map again. And yeah, we have a bunch of PIDs. Yeah, it's a bit shorter because I made it faster right now. So, and yeah, we can also check the logs. So BPF prog trace. Yeah, so we have like a bunch of forking processes and some new ones which just came up. So yeah, pretty much the same experience, but the loader is in Rust. But now I will show the example of Aya, which in which program the actual BPF program is different. Ooh. So here I have a bunch of subdirectories. The project tree here under Aya directory is auto-generated. They have a template which creates those 3 subdirectories. I didn't use the example common though. It's like just a boilerplate if you want to have some common library for something. But the 2 most important subdirectories are Aya example, which is our user space program, loading the BPF program, and here the actual BPF program, which is getting loaded. And the source code of the BPF program, as you can see, is in Rust. So it's doing the similar thing as the C code you've seen before, but yeah, we have a definition of map here, to which we are writing the PIDs. We have the common practice in Aya is that you write the main program just like as that one match unsafe thingy, and then you have separate unsafe function where you actually do stuff, because BPF programs, they will be always in unsafe context. So yeah, that's because of that. And yeah, in that BPF program, we are getting the PID, we are writing a log, and then inserting the PID into a BPF map. Yeah, we need to have, in case of BPF programs written in AI, you also need a separate panic handler, which you always assume that it's unreachable. And the loader part looks like it's loading slow. Come on. All right. And yeah, the cool thing about Aya, that's feature just came, I think, like 3 days ago, is that it has like the Aya log sublibrary, which is showing you the logs of BPF programs in your loader, and it's using underneath the perf event array, but yeah, it's doing it's automatically for you. It provides simple logging, which yeah, we will see later. And here is the initialization of it. Here we load the BPF program, and here we are getting the mutable reference to our particular program we are interested in, which is kernel clone. We then attach it to the kernel clone function, and yeah, here it's just like yeah, signal handling and showing dots that it's running. So yeah, let's check this out, how it works. Well, similar to the other examples I showed, but yeah, it's all Rust. So yeah, let's remove target. And here we have two commands. So we have an X task to build the BPF program first. So let's do that. Ooh. Cargo X task build eBPF. Yeah, it's taking some time. And yes, I mentioned it's using the internal LLVM inside Rust compiler. And yeah, now we can build the loader, which is you know, just with cargo. And yeah, as you can see, the user space part here is yeah, asynchronous. It's handled by Tokyo. And okay, we have it right now. So as a root, we are spawning the loader. It's in debug example, and then as an argument, we provide the BPF program to load, which is under target BPFL unknown debug and example. Okay, so yes, so it's running. It's showing some logs here, and yeah, let's check the content of the BPF map then. The situation should be pretty much the same. So we are going to have a hash map with processes, and we have two new BPF maps. That's internal stuff handled by Aya to show you the logs here in the output of user space program. So these two come from internal Aya sublibrary. And let's dump processes. Here the output is a bit different because I'm yeah, it's still in hex. It's in the hex format, but this should be pretty much like the same PIDs, similar PIDs to which which we are seeing in the PPF programmers and C. And yeah, of course, value is 0 because we always assign 0 here. We just assign um, the PID as a key. Funny thing, you know, AI is still super experimental, and the reason why the log message is only some process forked is that when I tried to log the actual PID, the program was crashing. So yeah, that's how experimental AI still is. There are definitely some bugs. Uh, but yeah, at least I managed to save PIDs in a BPF map, so that part worked. But logging it was not possible. All right. And okay, that was it when it comes to libraries in Rust for handling and writing BPF programs. Now I wanted to just tell a bit about the project I'm working recently. So I'm working also on quite fresh and experimental project called Loxy, which is trying to use eBPF LSM type of programs to make containers more secure. There is a phrase about containers. Containers do not contain, and that phrase means that contrary to popular belief, containers are not as secure as VMs, and they expose a lot of stuff from the host. And yeah, you can question whether it's necessary or not. But well, there are 2 points which are more important and like most frightening about containers today. Some file systems are not namespaced. So, okay, like when you create a container, you have some rootfs image of some other Linux distribution, cool. But some contents of /sys and some contents of /proc is the same. And to the degree that if you go into sys btrfs, for example, inside container, when you are running, when you are using btrfs as the file system on your host, then you are able to look up for metadata of your like host partition. When you are in a privileged container, you can normally use fdisk. You can see devices, you can see proc IRQ and stuff like that. And yeah, in my opinion, it's not really necessary. I would rather like the most of those subdirectories to be hidden from the inside container. So that's the one point which Loxy is going to tackle. The second point is that Docker, by default, without any plugins, allows you to mount everything inside container. And it includes also your slash directory from the host and Docker socket. And if you mount those inside the container, then yeah, you have pretty much passwordless sudo. And now combine it with the fact that usually in the most Docker installations, you have a Docker group and you add regular users to the Docker group so they can run containers. So even though someone is a regular user with sudo with password, he has granted for free passwordless sudo because he can just type docker run -v/ or mount the Docker sock. Yeah, it's possible. It's also possible to do chroots inside containers. So yeah, the goal of Loxy will be providing some kind of policies to prevent regular users from doing such actions. Yeah, the goal of this talk is not to go too deep into that project itself. Feel free to. I would be happy if you check out this project. But yeah, for now it's using libbpfrs because AI is lacking a support for LSM type of programs. But as soon as AI gets that support, I'm trying to work on that right now. I will be more than happy to rewrite everything in Rust and keep everything in Rust, not bother with C. So yeah, that was all from me in this talk. Thanks for listening. I hope you liked it. And yeah, do you have any questions?
Questions? Yeah, the person in the
How do eBPF programs written in Rust and C compare in size? For example, when you compiled that BPF program with Aya, I saw it compiled like the core library of Rust and so on. So I guess that's statically included. So how big are these things, and how does it compare between Rust and C?
Rust one is bigger, yes. It takes longer to compile also, and it statically links some parts of LLVM. So some parts of LLVM core library. So yes, the Rust BPF program is bigger.
Thank you for the presentation. So in the Aya example that you showed, you mentioned that the Rust code had to be explicitly marked as unsafe. Is it because it links against libbpf, or what is the requirement that Aya has that makes Rust code unsafe?
The thing is that BPF programs get the arguments from the kernel. So when we go to our program here, that context, you get it from the kernel, and that context contains a lot of pointers which point to the memory which kernel allocated. It's not Rust runtime. So yeah, that's because of dealing with pointers which we received from the kernel, and we have no idea like which size are these, and yeah, so that's because of yeah, we didn't handle that memory allocation ourselves here.
So you mentioned that eBPF programs are written in a bytecode, and I also noticed that they're loaded into ELF files. And I was wondering if you'd go into detail about what the bytecode is and why it's in an ELF file.
Much knowledge about that, about such a low level part of it. So yeah, I'm worried I will be not able to provide any like meaningful answers here. But yeah, usually the output of like compilation of BPF program by LLVM is like the O file, which has ELF sections, which has like the BPF program itself in a separate section, maps in separate sections, and yeah, and then it's getting loaded by libbpf into the kernel, and libbpf is also aware of like the ELF structure of it. I'm sorry, I'm not able to provide any more detailed answer than that.
Well, neither could I. So there's something to do with security and remembering that you don't have everything allowed in eBPF because it's in secure context. So the bytecode doesn't allow everything that C would allow you to do in that context. So you can't break things so much in the kernel.
Yeah, that's true. Yeah, and in BPF, inside the kernel, there's also a verifier. So when that bytecode is loaded into the kernel, it's not executed immediately, but first the verifier is checking whether you're, for example, not reaching the bounds of memory which kernel allocated for you. So it's firstly isolating, analyzing the whole bytecode, and when the verifier says, okay, that bytecode is safe, and okay, I can execute it without leaking memory, then it's executed.
So I didn't know about BPF before, and I just wanted to ask. I don't know if it's even right in the context, but is it constrained to any kernel version or like recent kernel versions?
Depends on the type of program. In general, eBPF, as we know it, started being available around like 4 point something. I would say like the oldest kernel which you can run to support the oldest type of network programs, for example, be able to use Cilium is like, I would say 4.18. You should it rather shouldn't go older than that. But then the more types of BPF programs started coming, they were coming in newer versions of the kernel. And for example, the LSM type of program, so the one which I'm using in LOXI came in kernel 5.7. So it differs on the type of program. The cool thing about BPF2 is that it provides probes, so it can list you what it checks your kernel, and it provides a list of what kind of BPF programs are supported, what kind of BPF maps are supported, and it also lists functions which you can use in BPF programs. So there is tooling around like checking what can be done with your kernel. But yeah, definitely the newer type of BPF program there are more constraints about new versions. And if you want to use the newest stuff from like last year, then I would say like 5 point something, 5.7 is necessary. But if you are dealing with networking, like tracing packets, redirecting them, doing some firewalling, DDoS protection, 4.18 should be fine.
One more. And one for the picture.
Okay, thank you. So you mentioned your personal project, LOXI. I also assume that you know AppArmor from Google. So how is it different, any different from AppArmor?
So LOXI is aware of each container which is running, and it's designed only for containers. And so far, my idea is to have 3 different policy levels for containers: restricted, baseline, and privileged. Where privileged will be really the kind of policy which could be applied only by root, and it will be discouraged to use it for anything else which is not Kubernetes infra, so like CNI plugins, Istio, service mesh, or whatever. The baseline and restricted will be like the most encouraged to use, and also able to be picked by regular users of Docker or Kubernetes. The difference is that, well, in AppArmor and SELinux, for example, in regards to mounting files into the container, from my knowledge, there is not really a way to differentiate what you can mount to each particular container. You are rather globally labeling directories which you can, in general, mount to the container. For example, in case of SELinux, you apply a label to some particular directory which you want to mount, but there is no differentiation or limitation to which particular container you can mount it. So there is not so much awareness about particular containers running. And on the other hand, in LOXI, I'm maintaining the BPF map containing all the containers running, then all the processes belonging on them. So when I get the event coming from some particular process, I'm able to look up for a concrete container and decide based on that what to do. And there is not so much awareness about particular containers in terms in AppArmor, SELinux, or SMAC, or any other LSM system.
No questions. Okay. Thank you so much for this talk.